Okay, so in yesterday's lecture, we have started the unit number 5, that is convection. And in convection, there are two bits, that is forced convection and natural convection. So, what is meant by convection? Convection is the mode of energy transfer between a solid surface and the adjacent liquid or gas that is in motion, and it involves the combined effect of conduction and fluid motion. Okay, so convection is nothing but transfer of heat because of the motion of the molecules, and due to that heat transfer is takes place. That type of mode is nothing but convection. Okay, basically two types of convection is there: forced convection and natural convection. What is the another name for the natural convection? That is free convection. Okay, so what is meant by free convection? Free convection is nothing but transfer of fluid takes place due to the डेन्सिटी डिफरन्स. म्हणजे फ्री कन्व्हेक्शन मध्ये काय असणार आहे, जे काय फ्लुइडला मोशन असणार आहे ते कशामुळे असणार आहे? बिकॉज ऑफ दी डेन्सिटी डिफरन्स. बिकॉज ऑफ दी डेन्सिटी difference, that is nothing but free convection. Okay, and what is meant by forced convection? Forced convection is nothing but transfer of fluid due to the external means. Transfer of fluid due to the external means such as fan, pump, blower, etc. ओके, इथं आपल्याला काय करायचं आहे? एक्सटर्नल डिव्हाइस यूज करायचा आहे, आणि त्या एक्सटर्नल डिव्हाइस मुळे काय होणार आहे, तर त्या फ्लुइडला मोशन प्राप्त होणार आहे. ओके, that is nothing but forced convection. So for that we have to use the external devices such as pump, blower, fan, etc. Okay, so this is about the types of the convection, that is natural convection and forced convection. After that we have discussed about the law of convection. As we know that what is the law related to convection? That is Newton's law of the cooling. Okay, and what is the statement of the Newton's law of the cooling? That is the heat transfer rate per unit area is directly proportional to the temperature difference. The heat transfer rate per unit area is directly proportional to the temperature difference. Means Q by A is directly proportional to the delta T, and from that we written the proportionality constant as a H. So we get the equation as a Q is equal to H into A into delta T. Q is equal to H into A into delta T. Okay, so this is the equation for the Newton's law of the cooling. By using that we have to calculate the rate of heat transfer for the convection. Rate of heat transfer by the convection. Okay, Q is nothing but heat transfer rate, A is nothing but surface area, delta T is nothing but temperature difference, and H is nothing but heat transfer coefficient. Okay, and we are considering one example, that is body is heated up to the certain temperature and its surface temperature is Ts, and is exposed to a cold fluid which is at temperature Ta, and Ts is greater than Ta. So from that we have written the equation for that. Q is equal to H into A into Ts minus Ta. Okay, and this heat transfer coefficient H is the function of different parameters. And what are these parameters? That is fluid flow. Okay, if fluid flow is laminar, if fluid flow is turbulent, if fluid flow is transition. Okay, so according to that we have to, so this is the first factor. Then second parameter, that is thermal properties of the fluid. So what are the thermal properties of the fluid? That is, what is the viscosity of the fluid, what is the density of the fluid, what is the thermal conductivity of the fluid, what is the specific heat of the fluid. Okay, so this is the second factor. Then third, geometry of the system. If plane wall is there, if cylinder is there, if sphere is there, according to that heat transfer coefficient is dependent on that particular factor. Then roughness of the solid surface, then orientation of the surface. Okay, so the heat transfer coefficient is the function of these parameters. Okay, these are the 5 parameters on which the heat transfer coefficient is depends. Okay, then the numerical value of the heat transfer coefficient is not uniform. Numerical value of the heat transfer coefficient is not uniform over the entire surface. जो काही आपण एखादा सरफेस कन्सिडर करणार आहे, तर त्या पर्टिक्युलर सरफेससाठी, टोटल सरफेससाठी हीट ट्रान्सफर कोएफिशियंट युनिफॉर्म नसणार आहे. ओके, इट इज डिपेंडंट ऑन ॲट विच लोकेशन वी हॅव टू मेजर दी टेम्परेचर. ज्या ठिकाणचं तुम्ही टेम्परेचर मेजर करताय त्या लोकेशनचा तुम्हाला हीट ट्रान्सफर कोएफिशियंट भेटू शकते. पण थ्रू आउट जर सरफेस जर विचार केला तर तो constant नसणार आहे. Okay, therefore equation 1 fails to give exact numerical value of the heat transfer coefficient. For calculating the exact value of H, we have to study different theories. Okay, so for the calculation of the exact value of H, we have to study the different theories, different mechanisms, dimensionless numbers, etc. टू अंडरस्टँड ऑल दिस वी मस्ट नो दी डायनॅमिक्स ऑफ द फ्लुइड फ्लो. तर हे समजून घेण्यासाठी आपल्याला काय माहिती पाहिजे, डायनॅमिक्स ऑफ द फ्लुइड फ्लो. ओके, सो इन दॅट वी हॅव discussed about the what is meant by the ideal fluid. So as we know that the fluid having no viscosity, ज्या फ्लुइडला विस्कॉसिटी नसणार आहे त्या फ्लुइडला काय म्हटलं जाते, आयडियल फ्लुइड म्हटलं जाते. ओके, सच फ्लुइड नॉट एक्झिस्ट इन दी नेचर, सच फ्लुइड नॉट एक्झिस्ट इन दी नेचर. ओके, then we have discussed about the real fluid. What is meant by real fluid? Real fluid is nothing but the fluid which possesses viscosity is known as the fluid which possesses viscosity is known as a real fluid. ओके, ज्या फ्लुइडला विस्कॉसिटी असणार आहे त्या फ्लुइडला काय म्हटलं जाते, तर रिअल फ्लुइड म्हटलं जाते. ओके, आफ्टर दॅट वी हॅव डिस्कस्ड अबाउट दी व्हॉट इज मीन बाय विस्कॉसिटी. विस्कॉसिटी इज नथिंग बट रेजिस्टन्स टू फ्लो. ओके, जी प्रॉपर्टी फ्लुइडची त्याच्या फ्लोला अपोज करणार आहे, रेजिस्ट करणार आहे, दॅट प्रॉपर्टी इज नथिंग बट viscosity. Okay, viscosity is primarily due to the cohesion and molecular movement exchange between fluid layers. Okay, in that top layer causes a shear stress on the adjacent bottom layer, while the lower layer causes a shear stress on the top layer. Okay, and from this is the shear stress directly proportional to the rate of change of velocity, that is tau is directly proportional to the du by dy. So tau is equal to mu into du by dy. Okay, so viscosity, from this we get the equation for the viscosity is equal to tau divided by du by dy, and from that we have written the definition for the viscosity, that is viscosity is also defined as the shear stress required to produce per unit rate of shear strain. Okay, and what are the units of the viscosity? That is SI unit is Newton second per meter square. Then what is the MKS unit? That is kgf second per meter square. What is the CGS unit? That is poise. Okay, so these are the units of the viscosity. Okay, now all of you write down the next point, that is kinematic viscosity. Write down the next point, kinematic viscosity. So as we know that what is meant by kinematic viscosity, kinematic viscosity is nothing but it is defined as the ratio of dynamic viscosity to the density of the fluid. Okay, it is defined as the ratio of dynamic viscosity to the density of the fluid. Okay, so write down the definition of the kinematic viscosity. Write down kinematic viscosity. It is defined as the ratio of dynamic viscosity to the density of the fluid. That is nu is equal to mu upon rho. Okay. What is the notation for the kinematic viscosity? That is nu. And for the dynamic viscosity, what is the unit? Mu. Notation mu. Okay. So nu is equal to mu upon rho. That is the kinematic viscosity. And what are the units of the kinematic viscosity? SI unit is meter square per second. Then MKS unit is meter square per second. And CGS unit is Stoke. CGS unit is Stoke. And as we know that 1 Stoke is equal to 10 raised to minus 4 meter square per second. 1 Stoke is equal to 10 raised to minus 4 meter square per second. Okay. So all of you write down this information related to the kinematic viscosity. Write down the definition. Write down the equation of the kinematic viscosity, and write down the units of the kinematic viscosity. Okay, so all of you completed this point, kinematic viscosity. So what are the units of the kinematic viscosity? SI unit is meter square per second, MKS unit is meter square per second, and CGS unit is Stoke. And what is the relation between Stoke and meter square per second? 1 Stoke is equal to 10 raised to minus 4 meter square per second. Okay, then write on the next point, laminar flow. Okay, so as we know that what is meant by laminar flow? Laminar flow is defined as the type of flow in which fluid particles move along a well-defined path or a streamline. Okay, well-defined path मध्ये जर फ्लुइड स्ट्रीम्स मूव्ह होत असतील तर त्या फ्लोला काय म्हटलं जातंय? लॅमिनर फ्लो म्हटलं जाते. किंवा त्याला कंडिशन काय आहे? इफ रेनॉल्ड्स नंबर इज लेस दॅन 2000 then we said that that flow is laminar flow. Okay, so all of you write down the first concept, that is laminar flow. laminar flow. Laminar flow. So write down the definition of the laminar flow. Laminar flow is defined as laminar flow is defined as okay. So for the laminar flow, what is the value of Reynolds number? Reynolds number is less than 2000. Then we said that that flow is laminar. Okay. So all of you write down the definition of the laminar flow and condition for the laminar flow. Okay. After that, we have to write down the next flow, that is turbulent flow. And as we know that what is meant by turbulent flow, the flow is said to be turbulent फ्लो इन विच पार्टिकल्स मूव्ह इन झिगझॅग वे. जर पार्टिकल झिगझॅग वे मध्ये मूव्ह होत असतील तर त्या फ्लोला काय म्हटलं जाते? दॅट फ्लो इज नथिंग बट टर्ब्युलंट फ्लो. ओके. अँड इन टर्ब्युलंट फ्लो द ईडीज फॉर्मेशन टेक्स प्लेस विच आर रिस्पॉन्सिबल फॉर हाय एनर्जी लॉस. टर्ब्युलंट फ्लो मध्ये एनर्जी लॉस कशामुळे होते? तर त्याच्यामध्ये मॅक्झिमम ईडीज फॉर्मेशन होते अँड बिकॉज ऑफ दॅट ईडीज the high energy losses takes place. And what is the condition for the turbulent flow? If Reynolds number is greater than 4000, at that time we said that that flow is nothing but turbulent flow. Okay. So all of you complete these two definitions and condition for that laminar flow and turbulent flow. Okay. Then write down the next point, next concept, that is boundary layer or hydrodynamic or velocity. Write down boundary layer concept or hydrodynamic layer concept or velocity layer concept. Okay. So write down. So this boundary layer concept was first introduced by scientist Prandtl in 1904. Okay, as applied to the fluid problems. So consider the flow of fluid past a thin stationary plate at a velocity v infinity under a no slip conditions. Okay, so we are considering the one plate is there, thin stationary plate, and velocity of the fluid v infinity under the no slip condition. Okay, so all of you write down the uh, new heading as a boundary layer concept, or what is the another name for that? Hydrodynamic layer or velocity layer. Write down. And this concept was introduced by the scientist Prandtl in 1904. Okay. And we are considering one thin plate and on which fluid is moving having velocities v infinity at the no slip condition. At the no slip condition. Okay, so write down the concept of boundary layer. The concept of boundary layer. The concept of boundary layer was first introduced. The concept of boundary layer was first introduced by L. Prandtl. Introduced by L. Prandtl in 1904. In 1904, as applied to fluid problems. As applied to as applied to fluid problems. As applied to fluid problems. Okay, full stop. Next para. Consider the flow of a fluid. Consider consider the flow of a fluid. Consider the flow of a fluid. Consider the flow of a fluid past a thin stationary plate. Consider the flow of a fluid past a thin stationary plate at a velocity v infinity. At a velocity v infinity under no slip condition. Under no slip condition. Under no slip condition. Under no slip condition. Okay, so all of you draw the diagram. Boundary layer concept. All of you draw this diagram. So in the boundary layer concept, we are considering one thin stationary plate and on which fluid is flowing, and in that there are three regions. Laminar flow is there, then transition zone is there, and turbulent zone is there. Okay, so the layer which is adjacent to the plate, because of the shear state, what will happen? It will resist upper layer to the lower layer. So at the leading edge, the velocity of that particular fluid stream is 0. Okay, so from that we get one layer, or we get one thickness. Okay, so all of you draw this diagram. We have to draw one plate, and on that plate we have to draw the first section as a laminar flow section, then second section as a transition zone section, and third section as a turbulent zone. That is A to B laminar flow, B to C transition zone, C to D turbulent zone. C to D turbulent zone. Okay, at the left hand side we have to denote the free stream velocity V infinity. Free stream velocity V infinity. Okay, and draw that graph A, E, F, G. Okay, in that laminar boundary layer is there and turbulent boundary layer is there. Okay, and A point is nothing but leading edge, and at the end that is trailing edge. Okay, and we have to denote the thickness of that velocity boundary layer as a dou. ओके. सो दिस इज दी व्हेलॉसिटी बाउंड्री लेअर. आपण लेअर कुठेपर्यंत ड्रॉ करत असते तिथली व्हेलॉसिटी काय असणार आहे 99% ऑफ दी फ्री स्ट्रीम व्हेलॉसिटी. ओके. अँड दॅट लाईन और दॅट थिकनेस इज नथिंग बट व्हेलॉसिटी or hydrodynamic boundary layer. Okay, and thickness of that particular is nothing but velocity thickness. ओके. तर ज्या प्लेटला ऍडजस्टंट जो लेअर असणार आहे तिथे काय असणार आहे नो स्लिप कंडिशन असणार आहे म्हणजे लिडिंग एज व्हेलॉसिटी 0 असणार आहे. ओके. त्याच्यानंतर जो दुसरा लेअर त्या लेअरला काय करणार आहे अपोज करणार आहे. सो इन दॅट वे वी गेट दी हायर व्हेलॉसिटी ऍज वी मुव्हिंग इन दी फॉरवर्ड डायरेक्शन. At the end we get the zero velocity and another upper layer will be retarded by the lower layer. So in that way after some times what will happen, the velocity will be increases and we get one graph that is nothing but velocity boundary layer, and thickness of that particular layer is nothing but velocity thickness. Okay. And we have drawn that line which is at the place where the velocity is 99% of the free stream velocity. म्हणजे जो काय आपण कर्व ड्रॉ केलेला आहे तो जो कर्व आहे तो कुठं आहे तर 99% व्हेलॉसिटी काय असणार आहे फ्री स्ट्रीमच्या म्हणजे फ्री स्ट्रीम म्हणजे व्ही इन्फिनिटीच्या 99% व्हेलॉसिटी असणार आहे. तिथं आपण तो ग्राफ ड्रॉ केलेला असणार आहे. त्याच्या आतमधली व्हेलॉसिटी काय असणार आहे जो काही ग्राफ आहे तो काय म्हटलं जातं त्याला व्हेलॉसिटी बाउंड्री लेअर. Okay, so write down first statement. When a real fluid flows past a stationary plate, एका स्टेशनरी प्लेट वरून आपण काय करणार आहे रिअल फ्लुइड फ्लो करणार आहे. ओके. when a real fluid flows past a stationary plate म्हणजे स्टेशनरी प्लेटला पास करून ते कुठे जाणार आहे पुढे जाणार आहे. ओके. past a stationary plate a layer of fluid which is in contact with boundary surface the boundary surface adheres to it on account of viscosity मुळे काय होणार आहे तर तिथं अपोज होणार आहे ऍट दी सरफेस ऑन अकाउंट ऑफ विस्कॉसिटी अँड कंडिशन ऑफ नो स्लीप ऑकर्स. नो स्लीप म्हणजे तिथं मोशन नसणार आहे. ओके. अँड कंडिशन ऑफ नो स्लीप ऑकर्स okay, full stop. And the velocity of a fluid at leading edge relative to plate becomes zero. समजलं बघा. जो काय प्लेटचा लिडिंग एज असणार आहे तिथं आपण जर फ्लुइड पास केलं तर तो फ्लुइड काय होणार आहे त्या फ्लुइडच्या विस्कॉसिटीमुळे तिथं रेझिस्टन्स क्रिएट होणार आहे आणि त्या सरफेसला व्हेलॉसिटी काय असणार आहे 0 असणार आहे. ओके. रिलेटिव्ह टू प्लेट becomes zero. Full stop. Okay. Then write down the next para. The adjacent layer also slow down. म्हणजे जो लेअर प्लेटला अटॅच असणार आहे त्याची व्हेलॉसिटी 0 होणार आहे पण त्याच्या आणखी ऍडजस्टला असणार आहे त्याच्याबद्दल आपण लिहितोय. ओके. द ऍडजसंट लेअर आल्सो स्लो डाऊन also slow down but a lower extent from the the adjacent layer also slow down, but a lower and lower extent from the boundary surface in y direction, lower extent from the boundary surface in y direction, and there exists a velocity gradient, म्हणजे velocity change होणार आहे with respect to distance, that is nothing but velocity gradient, and which is present in the y direction. Okay, in y direction, and there exists a velocity gradient, due to viscous effects, of the fluid, due to viscous effect of the fluid, due to the viscous effect of the fluid, full stop, due to viscous effect of the fluid, full stop. Next line, the fluid layer near the surface, the fluid layer, near the surface in which, the fluid layer near the surface in which there is general slowing down, the fluid layer near the surface in which there is general slowing down is defined as, velocity boundary layer, or hydrodynamic boundary layer, velocity boundary layer or hydrodynamic boundary layer. ओके, किंवा त्याला काय म्हटलं जाते, विस्कस किंवा जनरल बाउंड्री लेअर पण म्हटलं जाते त्याला. ओके, फुल स्टॉप. इन दिस लेअर, तर ह्या लेअर मध्ये काय होते बघा, इन दिस लेअर द व्हेलॉसिटी ऑफ फ्लो इन्क्रीजेस फ्रॉम झिरो व्हेलॉसिटी ऍट द सरफेस टू दी फ्री स्ट्रीम व्हेलॉसिटी ऍट द एज ऑफ द बाउंड्री लेअर. म्हणजे जिथपर्यंत ग्राफ ड्रॉ केलेला आहे त्याच्या आतमधली व्हेलॉसिटी ही फ्री स्ट्रीम पेक्षा कमी असणार आहे. ओके, आणि ज्या लाईन जी ड्रॉ केलेली आहे कर्व, तिथून पलीकडे काय होणार आहे, व्हेलॉसिटी फ्री स्ट्रीम एवढी असणार आहे. ओके, सो राईट डाऊन, इन दिस लेअर, the velocity of flow, in this layer the velocity of flow, increases from, in this layer the velocity of flow increases from zero velocity at the surface, to the free stream velocity at the edge of the boundary layer. In this layer, the velocity of flow increases from zero velocity at the surface to the free stream velocity at the edge of boundary layer. Okay. So how to calculate the dou? What is the thickness of that particular boundary layer? And what is that thickness of the boundary layer? The thickness of the boundary layer is generally defined as a distance from the surface at which local velocity is 99% of the free stream velocity. Okay, boundary layer, velocity boundary layer thickness म्हणजे डो असणार आहे. आणि डो कसा फाइंड आउट करणार आहे, तर त्याची जी काही व्हेलॉसिटी असणार आहे, द थिकनेस ऑफ द बाउंड्री लेयर डो इज जनरली डिफाइंड एज द distance from the surface at which local velocity is 99% of the free stream velocity. ओके, लोकल वेलॉसिटी जर 99% असेल फ्री स्ट्रीमच्या, तर ती तो जो थिकनेस असणार आहे त्या टायमिंगला, दॅट थिकनेस इज नथिंग बट वेलॉसिटी thickness of that boundary layer. Okay, so write down this, the thickness of the boundary layer, dou is generally defined as, the thickness of the boundary layer dou is generally defined as a distance from the surface, distance from the surface at which local velocity v is equal to zero point 0.99 into free stream velocity. 0.99 into free stream velocity, that is v infinity. Okay, so write down that equation. V is equal to 0.99 into v infinity. Okay, so this is the definition for the thickness of the boundary layer. Okay, then write down the thickness of the boundary layer dou increases due to. आता हा डो ची व्हॅल्यू इन्क्रीज होत जाणार आहे, तर त्याचं रिझन काय असणार आहे बघा. लेफ्ट हँड साइडला डो ची व्हॅल्यू कमी आहे, जसं जसं पुढे जाईल तशी डो ची व्हॅल्यू इन्क्रीज होणार. ओके, सो थिकनेस ऑफ द बाउंड्री लेयर डो इन्क्रीजेस ड्यू टू कंटिन्युअस रिटार्डेशन ऑफ द फ्लो. तर ह्या फ्लोला जो काय आहे त्याला कंटिन्युअसली अपोज होणार आहे. And because of this retardation, what will happen? The thickness of that boundary layer will be increases. Okay, the thickness of the boundary layer dou increases. The thickness of the boundary layer dou increases due to continuous retardation of flow. Due to continuous retardation of flow. Continuous retardation of flow, full stop. The flow is laminar initially. The flow is laminar initially. The flow is laminar initially, and there is no intermixing of layers. And there is no intermixing of layers. ओके, सो देअरफॉर पहिला लेअर जो असणार आहे तो लॅमिनर लेअर असं म्हटलेलं आहे, कारण तिथे जे काही लेयर्स असणार आहेत त्याचं इंटरमिक्सिंग होणार नाही. ओके, व्हॉट इज मीन बाय लॅमिनर फ्लो? लॅमिनर फ्लो इज नथिंग बट द फ्लो इन विच फ्लुइड पार्टिकल्स मूव्ह इन ए वेल डिफाइन्ड पाथ. ओके, जे काही स्ट्रीम लेयर्स असणार आहेत ते एका वेल डिफाइन्ड पाथ मध्ये मूव्ह होणार आहेत, इंटरमिक्सिंग नसणार आहे. ओके, इनिशियली देयर इज ए नो इंटरमिक्सिंग ऑफ द लेयर्स, फुल स्टॉप. The velocity variation is parabolic in laminar flow region. The velocity variation is parabolic in laminar flow region. Laminar flow region. Laminar flow region. Laminar flow region. Full stop. Momentum transfer is at the molecular level. Momentum transfer is at the molecular level, mainly by diffusion. Mainly by diffusion. Full stop. The viscous forces are large compared to inertia forces in this region. The viscous forces are large. The viscous forces are large compared to inertia forces. Viscous forces are large compared to inertia forces in this region. In this region. Full stop. Next line. Beyond a certain distance, the flow in the boundary layer, beyond a certain distance, the flow in the boundary layer becomes turbulent. The flow in the boundary layer becomes turbulent with macroscopic mixing of layers. ओके, पहिला लेअर जो असणार आहे तो लॅमिनर लेअर असणार आहे. त्याच्यानंतर काय असणार आहे, सर्टन डिस्टन्स नंतर टर्ब्युलंट होणार आहे, कारण तिथे मिक्सिंग ऑफ लेयर्स होणार आहे. ओके, सो राईट ऑन बियॉन्ड ए सर्टन डिस्टन्स द फ्लो इन द बाउंड्री लेअर becomes turbulent with macroscopic mixing of layers with macroscopic mixing of layers macroscopic mixing of layers macroscopic mixing of layers full stop. Inertia forces overcome the viscous force पेक्षा inertia force काय होणार आहे, इन्क्रीज होणार आहे. inertia forces overcome the viscous forces inertia forces overcome the viscous forces full stop. Next line, this change from laminar to turbulent flow this change from laminar to turbulent flow occurs at a value of this change from laminar to turbulent flow occurs at a value of this change from laminar to turbulent flow occurs at a value of Reynolds number at about Reynolds number at about Reynolds number at about 5 into 10 raised to 5 5 into 10 raised to 5 in case of 5 into 10 raised to 5 in case of flow over the flat surfaces flow over the flat surfaces. Okay, and how to calculate this Reynolds number? As we know that Reynolds number is equal to V into X divided by nu. किंवा स्टँडर्ड इक्वेशन काय रेनॉल्ड्स नंबरचं, रो व्ही डी बाय म्यू. तेच इक्वेशन कसं लिहू शकतो आपण, व्ही इंटू एक्स डिवायडेड बाय न्यू. कारण न्यू म्हणजेच काय असतंय, कायनॅमेटिक विस्कॉसिटी म्हणजे डायनॅमिक विस्कॉसिटी डिवायडेड बाय डेन्सिटी. ओके, सो राईट ऑन द इक्वेशन ऑफ द रेनॉल्ड्स नंबर, राईट डाउन रेनॉल्ड्स number is equal to V into X divided by nu. So this is the equation which is useful for the flat plate. पाईप असेल तर डायमीटर येत असतोय, प्लेट असेल तर थिकनेस येत असतोय x. ओके, सो रेनॉल्ड्स नंबर इज इक्वल टू V into X divided by nu. Okay, so this is about the boundary layer concept or hydrodynamic boundary layer or velocity boundary layer. Okay, then write down the next point, thermal boundary layer. Okay, all of you write down next point, that is thermal boundary layer. ओके, जसं व्हेलॉसिटीचं व्हेरिएशन असणार आहे तसं टेम्परेचरचं पण काय असणार आहे, व्हेरिएशन असणार आहे. ओके, म्हणजे प्लेटचं टेम्परेचर वेगळं, त्याच्यानंतर फ्लुइडचं टेम्परेचर वेगळं, अँड बिकॉज ऑफ दिस व्हॉट विल हॅपन, देर इज ए फॉर्मेशन ऑफ थर्मल बाउंड्री लेअर. ओके, इफ देर आर टू कंडिशन्स आर पॉसिबल, म्हणजे जे काही टेम्परेचर आहे फ्लुइडचं आणि जे काही सरफेसचं टेम्परेचर आहे, समजा फ्लुइडचं टेम्परेचर जास्त असेल ती एक केस असणार आहे आणि सरफेसचं टेम्परेचर जास्त असणार आहे ती एक केस असणार आहे. सो फॉर दॅट पर्टिक्युलर केस वी हॅव टू ड्रॉ दी थर्मल बाउंड्री लेअर. ओके, त्याच्या आतमधली म्हणजे त्या जिथं आपण ग्राफ ड्रॉ करणार आहे त्याच्या आतमधली जी काही टेम्परेचर असणार आहे फ्लुइडचं ते वेगळं असणार आहे ऍज कम्पेअर टू दी टेम्परेचर ऑफ दी फ्लुइड. Okay, so we have to draw that line. That line mentions that after that there is a same temperature, but if we have coming inside that particular line there is a difference in the temperature. Okay, so all of you write down the information related to the thermal boundary layer. Write down, there is development of write down thermal boundary layer. There is development of there is a development of thermal boundary layer, thermal boundary, there is development of thermal boundary free stream layer, there is a development of thermal boundary free stream layer analogous to velocity boundary layer, 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 analogous to velocity boundary layer. If the temperature of the fluid, if the temperature of the fluid, if the temperature of the fluid, if the temperature of the fluid T infinity, फ्लुइडच्या टेम्परेचरला काय म्हटलेलं आहे T infinity is different from the solid surface temperature, T infinity is different from the solid surface temperature Ts, different from the solid surface temperature Ts as shown in figure, as shown in figure, as shown in figure for cases, as shown in figure for cases T infinity is less than Ts. आपण दोन केस कन्सिडर करणार आहे T infinity is less than Ts and T infinity is greater than Ts. T infinity is greater than Ts. Okay. So for that particular we have to draw the thermal boundary layer. Okay. जो काय ग्राफ असणार आहे तो सेम असणार आहे पण जे काही टेम्परेचरचं प्रोफाईल असणार आहे ते कसं असणार आहे वेगवेगळं असणार आहे फॉर दी T infinity is less than Ts and T infinity is greater than Ts. Okay, so all of you draw the two cases, case 1 and case 2. So case 1 is nothing but flow of fluid over a hot plate and case B is nothing but flow of fluid over the cold plate. Okay, म्हणजे पहिल्या केस मध्ये T infinity कमी आहे as compared to the Ts and second case मध्ये T infinity जास्त आहे as compared to the Ts. So all of you draw these two diagrams, case 1 and case 2, that is case A and case B. ओके, जे काय फ्लुइड आहे त्याची व्हेलॉसिटी V इन्फिनिटी, त्याचं टेम्परेचर T इन्फिनिटी. ओके, आणि त्याच्यानंतर थर्मल बाउंड्री लेअर येणार, त्याच्या आतमध्ये काय दाखवलेलं आपण टेम्परेचर. ओके, सो इनसाइड दॅट पर्टिक्युलर कर्व देयर इज ए okay, and similarly for the case 2 now to draw the temperature profile. Salim Sheikh, mute yourself. Salim Sheikh, stop your audio. Yes sir, mute Salim Sheikh. Okay, so all of you draw this diagram. Draw case A and case B. Case A is nothing but T infinity is less than Ts, म्हणजे सरफेसचं टेम्परेचर जास्त असणार, म्हणजे हॉट प्लेट असणार आहे आणि त्याच्यावर आपण काय करणार आहे फ्लुइड मूव्ह करणार आहे. आणि सेकंड केस मध्ये प्लेट जी असणार आहे ती कोल्ड असणार आहे आणि त्याच्यावर आपण हॉट फ्लुइड मूव्ह करणार आहे. ओके, फॉर दिस टू कंडिशन्स वी हॅव टू ड्रॉ द टेम्परेचर प्रोफाइल. ओके, ओके. तर बघा, ज्या वेळेला हॉट प्लेट वरून आपण फ्लुइड पास करणार आहे त्यावेळेला काय होणार आहे, हॉट प्लेटला जो ऍडजस्टंट लेअर असणार आहे त्याचं टेम्परेचर आणि सरफेसचं टेम्परेचर काय होणार आहे, सेम होणार आहे. आणि तो जिथपर्यंत आपण कर्व ड्रॉ केलेला असतोय तिथपर्यंत काय होत असते, तर टेम्परेचर व्हेरिएशन असते. अँड आफ्टर दॅट कर्व देअर इज ए सेम टेम्परेचर ऑफ द फ्लुइड is possible. Okay, so temperature profile is continuously reducing over that particular plate for the T infinity is less than Ts, and for the second condition, that is T infinity is greater than Ts, what will happen, the temperature is continuously increases. Okay, because plate is cold but fluid is having more temperature as compared to the plate, so because of that we get the that graphical representation is denoted in the diagram B. So all have to draw these two diagrams. Okay, so write down. Write down. Consider the flow of fluid. Write down next line. Consider the flow of fluid. Consider the flow of fluid over a plate. Consider the flow of fluid over a plate. Over a plate. When the pre-steam temperature is T infinity. Consider the flow of fluid over a plate when the pre-stream temperature is T infinity. Pre-stream temperature is T infinity. And the surface temperature is Ts. And surface temperature is Ts. Surface temperature is Ts. In case Ts is greater than T infinity. In case Ts is greater than T infinity, as shown in figure A, Ts is greater than T infinity as shown in figure A, the fluid particles adjacent layer to plate, the fluid particles adjacent layer to plate will get the same temperature. आता आपल्याला माहिती आहे प्लेटच्या जे कॉन्टॅक्ट मध्ये जे लिक्विड येणार आहे त्याचं टेम्परेचर त्या प्लेट इतकंच होणार आहे. ओके, fluid particles adjacent layer to plate will get the same temperature as of plate, same temperature as of plate, where the fluid particles have zero velocity, where the fluid particles have zero velocity, full stop. It should be noted that at leading edge, the temperature profile is same. At the leading edge, the temperature profile is the same. म्हणजे काय असणार आहे, that is Ts is equal to T infinity. Ts is equal to T infinity. Ts is equal to T infinity. Full stop. The next para. The fluid particles coming in contact with surface, the fluid particles coming in contact with surface, the fluid particles coming in contact with surface, the fluid particles coming in contact with surface will exchange heat energy, will exchange heat energy, will exchange heat energy, will exchange heat energy with the adjacent layers, will exchange heat energy with the adjacent layers of fluid, adjacent layers of fluid, adjacent layers of fluid, and so on, adjacent layers of fluid, and so on, and so on. As a result, as a result, a thermal gradient, as a result, as a result, a thermal gradient is set up, as a result, a thermal gradient is set up in the fluid layer, thermal gradient is set up in the fluid layer, thereby, thereby a temperature profile is developed, thereby a temperature profile, thereby a temperature profile is developed, temperature profile is developed in the fluid flow, temperature profile is developed in the fluid flow, in the fluid flow, full stop. The heat is conducted by conduction, the heat is conducted, the heat is conducted by conduction, the heat is conducted by conduction. Okay, and what is the definition of this thermal boundary layer? Okay, किंवा ते thickness, how to calculate the thickness? The thickness of the thermal boundary layer at any point along the flow direction is defined as a distance y from the plate surface at which the temperature difference Ts minus T is 0.99 times the Ts minus T infinity. जसं आपण व्हेलॉसिटी मध्ये म्हणतोय की लोकल व्हेलॉसिटी 99% जर फ्री स्ट्रीम एवढी असेल तसंच टेम्परेचरचं पण आहे. म्हणजे हा जो टेम्परेचर डिफरन्स असणार आहे टीएस मायनस टी, हा टेम्परेचर डिफरन्स 99% ऑफ टीएस मायनस टी इन्फिनिटी जर असेल, then we said that that thickness is nothing but thermal boundary layer thickness. Okay, so write down the definition, definition of thermal boundary layer, write down definition of thermal boundary layer, definition of thermal boundary layer, definition of thermal boundary layer. The flow region over the surface, the flow region over the surface, the flow region over the surface having the temperature variation, having the temperature variation, having the temperature variation in the direction perpendicular to surface, temperature variation in the direction perpendicular to surface, perpendicular to surface is called the thermal boundary layer, is called the thermal boundary layer, is called the thermal boundary layer, thermal boundary layer, full stop. Next line, write down the definition. The thickness of thermal boundary layer, the thickness of boundary, thermal boundary layer, dou T, the thickness of thermal boundary layer, the thickness of thermal boundary layer dou T at any point, the thickness of thermal boundary layer dou T at any point along the flow direction at any point along the flow direction is defined as distance y from the plate is defined as distance y from the plate surface distance y from the plate surface distance y from the plate surface at which the temperature difference Ts minus T is at which the temperature difference Ts minus T is 0.99 times 0.99 times the Ts minus T infinity Ts minus T infinity Ts minus T infinity when Tw is greater than T infinity Tw is greater than T infinity and write down the equation for the theta. Theta is equal to Ts minus T divided by Ts minus T infinity is equal to 0.99. When this condition is satisfied, at that time thickness is nothing but thermal boundary layer thickness. Okay, so write down theta is equal to Ts minus T divided by Ts minus T infinity is equal to 0.99. Okay, then write on the next point significance of this velocity and thermal boundary layer. ओके, तर आपल्याला माहिती आहे की व्हेलॉसिटी जर कंटिन्युअसली चेंज होत असेल तर व्हेलॉसिटी बाउंड्री लेयर क्रिएट होणार आहे. टेम्परेचर कंटिन्युअसली चेंज होत असेल तर थर्मल बाउंड्री लेयर क्रिएट होणार आहे. ओके, and what is the significance of this velocity and thermal boundary layer? So there are different fluids are there, liquid is there, gas is there. So for that particular condition we have to understood what is the value of thermal boundary layer, what is the value of velocity boundary layer, what is the relation between thermal boundary layer and velocity boundary layer thickness. Okay, so according to that thermal boundary layer thickness, velocity boundary layer thickness, we have to understood the significance of that particular velocity and thermal boundary layer. Okay, means we have to understood which effect is more, means thermal effect is more or viscous effect is more. So we have to understood this by using this थर्मल अँड व्हेलॉसिटी बाउंड्री लेअर. ह्याच्यावरून आपण काय फाइंड आउट करू शकतोय की कुठला इफेक्ट जास्त असणार आहे, विस्कस इफेक्ट जास्त असणार आहे की थर्मल इफेक्ट जास्त असणार आहे. सो दॅट वी हॅव टू अंडरस्टूड बाय युझिंग दिस सिग्निफिकन्स ऑफ द व्हेलॉसिटी अँड थर्मल बाउंड्री लेअर. ओके, सो ऑल ऑफ यू राइट डाउन द नेक्स्ट पॉइंट significance of velocity and thermal boundary layer. Significance of velocity and thermal boundary layer. Significance of velocity and thermal boundary layer. Okay, so write down. The growth of velocity boundary layer dou is due to velocity gradient. तेच आहे बघा, the growth of velocity boundary layer dou is due to velocity gradient caused by viscous friction. The growth of velocity boundary layer dou is due to velocity gradient caused by viscous friction while the growth of thermal boundary layer dou T while the growth of thermal boundary layer dou T is due to temperature gradient. The growth of thermal boundary layer dou T is due to temperature gradient caused by heat transfer. Thermal boundary layer dou T is due to temperature gradient caused by heat transfer. Caused by heat transfer. Full stop. Next para. Both the boundary layer will be developed simultaneously. Both the boundary layer. Both the boundary layer will be developed simultaneously. Both the boundary layer will be developed simultaneously. Developed simultaneously whenever the temperature difference exists. Whenever the temperature difference exists. Whenever the temperature difference exists between the free stream fluid temperature. Between the free stream fluid temperature and the surface temperature. And the surface temperature. And the surface temperature. Okay, the next line. In case the viscous effects are higher. ज्याला विस्कस इफेक्ट हायर असणार आहे थर्मल इफेक्ट पेक्षा त्याला व्हेलॉसिटी बाउंड्री लेयर तुम्हाला थिकर भेटणार आहे ॲज कम्पेअर टू दी थर्मल बाउंड्री लेयर. ओके, दॅट रिटन इन दॅट स्टेटमेंट. इन केस द विस्कस इफेक्ट्स आर हायर दॅन दी थर्मल इफेक्ट्स. इन केस द विस्कस इफेक्ट्स आर हायर दॅन थर्मल इफेक्ट्स. In case the viscous effects are higher than thermal effects. Higher than thermal effects, the velocity boundary dou will be thicker than. The velocity boundary dou will be thicker than the thermal boundary layer dou T. Thicker than the thermal boundary layer dou T, and vice versa. Thermal boundary layer dou T and vice versa. And vice versa. Full stop. The relative thickness of velocity boundary layer. Boundary thickness. The relative thickness of velocity boundary thickness dou and thermal boundary thickness dou T. The relative thickness of velocity boundary thickness dou and thermal boundary thickness dou T depends on the Prandtl number. Depends on the Prandtl number of the fluid. Prandtl number of the fluid. Prandtl number of the fluid. ओके, म्हणजे प्रँटल नंबर 1 असेल तर काय असणार आहे, दोन्हीचा थिकनेस सेम असणार आहे. ओके, सो राईट डाऊन. व्हेन प्रँटल नंबर इज इक्वल टू 1. When Prandtl number is equal to 1, then velocity boundary thickness and thermal boundary thickness should be same. Okay, so when Prandtl number is equal to 1, when Prandtl number is equal to 1, then dou is equal to dou T. Velocity boundary thickness is equal to thermal boundary thickness. Then when Prandtl number is less than 1, Prandtl number is less than 1, then dou T is greater than dou. Prandtl number ज्यावेळेला 1 पेक्षा कमी असणार आहे त्यावेळेला थर्मल बाउंड्री लेयरचा थिकनेस जो असणार आहे तो जास्त असणार ॲज कम्पेअर टू दी velocity boundary layer thickness. Okay, Prandtl number is less than 1, then dou T is greater than dou. Thus the relative thickness of boundary layer. Thus the relative thickness of boundary layers. Thus the relative thickness of boundary layers depends on the type of fluid. Thus the relative thickness of boundary layers depends on the type of fluid. Depends on the type of fluid. Okay, write down the A condition in case of liquid and gases. तर त्याच्यासाठी आपल्याला त्याचं रिलेशन काय असायचं बघणार आहे. इन केस ऑफ लिक्विड अँड गॅसेस, तर त्यावेळेला थर्मल बाउंड्री लेअर थिकनेस हा जास्त असणार ॲज कम्पेअर टू दी व्हेलॉसिटी बाउंड्री लेअर थिकनेस. ओके, सो राईट डाऊन इन केस ऑफ लिक्विड अँड गॅसेस, in case of liquid and gases, dou T is greater than dou T is greater than dou, since thermal effects are more pronounced than viscous effects. Dou T is greater than dou, since thermal effects are more pronounced than viscous effects. Thermal effects are more pronounced than viscous effects for the liquid and gases. Okay, dou T is greater than dou. And write on B, in case of oils and grease. In case of oils and greases, dou T is less than dou, dou T is less than dou, dou T is less than dou, since viscous effects are more pronounced, since viscous effects are more pronounced than thermal effects, since viscous effects are more pronounced than thermal effects, more pronounced than thermal effects. ओके, जर लिक्विड आणि गॅसेस असेल त्यावेळेला थर्मल इफेक्ट हा जास्त असणार ॲज कम्पेअर टू विस्कस इफेक्ट, आणि ऑइल आणि ग्रीस मध्ये काय असणार आहे, व्हेलॉसिटी इफेक्ट जो असणार आहे तो, विस्कस इफेक्ट जो असणार आहे तो जास्त असणार ॲज कम्पेअर टू दी थर्मल इफेक्ट. ओके, सो राईट डाऊन द व्हेरिएशन ऑफ डो अँड डो टी विथ व्हेरिएशन इन प्रँटल नंबर. प्रँटल नंबरच्या व्हेरिएशन वरती डो आणि डो टी ची कशी डिपेंडंट आहे ते आपण ड्रॉ केलेलं आहे. द व्हेरिएशन ऑफ डो अँड डो टी, द व्हेरिएशन ऑफ डो अँड डो टी with variations in Prandtl number, with variations in Prandtl number, with variations in Prandtl number. So write down, draw this graph, graphical representation, x-axis, y-axis. For the x-axis, distance x is there, at the center x is equal to 0, dou t is there. So Prandtl number is less than 1, Prandtl number is 1, Prandtl number is greater than 1. For that we have to draw the curve. So Prandtl number is less than 1 means dou t is greater than dou. Prandtl number is 1 is nothing but dou is equal to dou t, and Prandtl number is greater than 1 is nothing but dou t is less than dou. Okay, so all of you write down the relation for the Prandtl number. Relation for the Prandtl number. Okay, so this is the significance of the velocity and thermal boundary layer. म्हणजे प्रँटल नंबर वरून आपल्याला समजते की कुठला थिकनेस जास्त असणार आहे किंवा कुठला इफेक्ट जास्त असणार आहे, विस्कस इफेक्ट जास्त असणार आहे की थर्मल इफेक्ट जास्त असणार आहे. ओके, देन राईट डाऊन दी नेक्स्ट हेडिंग, मीन फिल्म टेम्परेचर और रेफरन्स टेम्परेचर. मीन फिल्म टेम्परेचर और रेफरन्स टेम्परेचर. मीन फिल्म टेम्परेचर और reference temperature. Give the new heading, mean film temperature or reference temperature. ओके, आता बघा एखादी प्लेट आहे त्याच्यावर आपण जर फ्लुइड प्लास केलं तर फ्लुइडचं टेम्परेचर वेगळं असते आणि त्या प्लेटचं टेम्परेचर वेगळं असते. तर त्या थर्मल बाउंड्री लेअर मध्ये ते टेम्परेचर व्हेरिएशन असणार आहे. तर मीन फिल्म टेम्परेचर म्हणजे आपल्याला काय करायचं आहे, फॉर दी करेक्ट अनालिसिस वी हॅव टू टेक दी average of the surface and fluid temperature. Okay, so all of you write down the one statement, write down directly second paragraph, write down what is the mean film temperature or reference temperature. Write down only second paragraph we have to write down. In order to carry out the convective heat transfer analysis, in order to carry out in order to carry out the convective heat transfer analysis, in order to carry out the convective heat transfer analysis, convective heat transfer analysis, and to calculate the mean heat transfer coefficient, and to calculate the mean heat transfer coefficient, and calculate the mean heat transfer coefficient, the mean temperature of the mean temperature of the mean temperature of the surface and that of fluid, the mean temperature of the surface and that of fluid is taken into account, is taken into account, is taken into account, is taken into account. ओके, तर ह्या दोन्हीचं टेम्परेचर आपल्याला कन्सिडर केलं पाहिजे. कशा कशाचं, त्या सरफेसचं आणि फ्लुइडचं, आणि त्याच्यावरचं अवरेज घेऊन ते जे टेम्परेचर असणार आहे त्याला मीन फिल्म टेम्परेचर म्हटलं जाते. ओके, सो नेक्स्ट हेडिंग राईट डाऊन कॅरेक्टरिस्टिक लेंथ और इक्विव्हॅलेंट डायमीटर, characteristic length or equivalent diameter, characteristic length or equivalent diameter, ओके. तर कॅरेक्टरिस्टिक लेंथ किंवा इक्विव्हॅलेंट डायमीटर, काही शेप जे असणार आहेत ते कॉम्प्लिकेटेड शेप्स असणार आहेत, तर त्याचं कन्व्हर्जन आपल्याला इक्विव्हॅलेंट डायमीटर मध्ये करायचं आहे. म्हणजे त्या शेपचं सेपरेट कॅल्क्युलेशन करण्यापेक्षा आपण जर इक्विव्हॅलेंट डायमीटर त्याचा फाइंड आउट केला आणि ते जर इक्वेशन मध्ये यूज केलं तर ते सिम्पल होणार आहे. म्हणजे ज्या काही कॉम्प्लिकेटेड जॉमेट्रीज आहेत, देर आर सम ऑफ दी कॉम्प्लिकेटेड जॉमेट्रीज, and for the analysis of that particular geometry there is a need to convert that complicated geometry into a diameter or into a tube or into a pipe. Okay, and from that pipe we have to calculate the equivalent diameter so that the calculations are easy. समजलंय बघा, हा इक्विव्हॅलेंट डायमीटरचा किंवा कॅरेक्टरिस्टिक लेंथचा जो काही कन्सेप्ट आहे, जे काही कॉम्प्लिकेटेड शेप्स आहेत तिथे आपण डायरेक्ट कॅल्क्युलेशन करू शकत नाही, डायरेक्ट त्याचं अनालिसिस करू शकत नाही. म्हणून ती जी कॉम्प्लिकेटेड शेप असते त्याला एका पर्टिक्युलर ट्यूब मध्ये किंवा पाईप मध्ये कन्वर्ट केलं जाते. मग त्या कन्व्हर्जन साठी आपण एक कन्सेप्ट समोर आणतो, दॅट कन्सेप्ट इज नथिंग बट इक्विव्हॅलेंट डायमीटर. ओके, सो all of you take the screenshot of this page and we have to write down by your own, and directly you have to go for the equations. So write down the equation. From that, write down the equivalent diameter is usually defined as, from the equation we have to write. समजले बघा, कॉम्प्लिकेटेड शेप मध्ये जर अनालिसिस करायचं असेल तर त्याचं कन्व्हर्जन इक्विव्हॅलेंट डायमीटर मध्ये करायचं असते. आणि तो इक्विव्हॅलेंट डायमीटर कसा फाइंड आउट करायचा, त्याचे काहीतरी इक्वेशन्स आहेत. त्याचं इक्वेशन काय आहे तर 4ac/p. तर ह्या इक्वेशनचा यूज करून आपण त्या कॉम्प्लिकेटेड शेपचा इक्विव्हॅलेंट डायमीटर फाइंड आउट करू शकतो, आणि त्याच्यावरून आपल्याला काय मिळणार आहे, हीट ट्रान्सफर कोएफिशियंट मिळणार आहे. Okay, so that information is given in this paragraph. So all of you write down this paragraph by your own. So all of you take the screenshot of this page. Okay, so from the equations we have to write down what is meant by the equivalent diameter. So write down the equivalent diameter is usually defined as, the equivalent diameter is usually defined as, the equivalent diameter is usually defined as, तर काय इक्वेशन बघा, इक्विव्हॅलेंट डायमीटर D is equal to 4 into AC divided by P. Okay, AC is nothing but cross sectional area, P is nothing but perimeter. Okay, तर हे इक्वेशन मध्ये जर तुम्ही व्हॅल्यू पुट केला तर तुम्हाला दिसतंय की we get the value as a D, that D is nothing but inner diameter of the tube. Okay, so write down this equation, D is equal to 4AC by P. AC is nothing but cross sectional area and P is nothing but perimeter. Then write down it is used for, it is used for solve the problems of, it is used for, it is used for solve the problems of, solve the problems of pressure drop and heat transfer coefficient, It is used for solve the problems of pressure drop and heat transfer coefficient heat transfer coefficient. Okay, now we have to find out the equivalent diameter for the different geometries. Okay, so first geometry, all of you consider first geometry as a, for rectangular duct we have to find out the value of equivalent diameter. So write down, for rectangular duct for rectangular duct. Okay, so all of you draw one diagram having width is b, length is l. रेक्टँग्युलर डक्ट साठी आपल्याला काय फाइंड आउट करायचं आहे, म्हणजे एक शेप आहे आपल्याकडे रेक्टँग्युलर डक्ट आहे समजा, तर त्याचा आपल्याला जर हीट ट्रान्सफर कोएफिशियंट फाइंड आउट करायचं असेल तर पहिला आपण त्या डक्टचं कन्व्हर्जन कशामध्ये करणार आहे, ट्यूब मध्ये करणार आहे किंवा पाईप मध्ये करणार आहे. So for that calculation we have to find out that equivalent diameter. Okay, and how to find out that equivalent diameter? That is D is equal to 4 into AC divided by P. Okay, so cross section area of the rectangular duct, that is L into B, and what is the perimeter of the rectangular duct, that is 2 into bracket L plus B. Okay, so all of you draw this diagram for the rectangular duct. Use that equation, D is equal to 4 into AC by P. What is the cross section area for the rectangle, that is L into B. What is the perimeter for the rectangular, that is 2 into bracket L plus B. So from this we get the equation for the equivalent diameter as a 2 into L into B divided by L plus B. Okay, so this is the equivalent diameter for the rectangular duct. Okay, all of you understood how to calculate the equivalent diameter? There is a one standard equation, 4 into AC by P, and by using that we have to calculate the equivalent diameter. So for the rectangular duct we get the value as a 2 into L into B divided by L plus B. Okay, now we have to consider the second geometry, that is for rectangular annulus. Write down the second shape for rectangular annulus. So draw this diagram for rectangular annulus. म्हणजे मधला स्पेस मोकळा असणार आहे, त्याचं थिकनेस विड्थ लेंथ आणि विड्थ दिलेले आहे L2 into B2 आणि बाहेरची लेंथ इंटू विड्थ दिलेली आहे L1 into B1. So for this we have to calculate the equivalent diameter. Okay, so as we know that what is the standard equation, equivalent diameter is equal to 4 into AC divided by P. So all of you put the values into this equation and find out the value of equivalent diameter for the rectangular annulus. Okay. So what is the equation for the rectangular annulus? 4 into AC by P. So what is the cross section area for the rectangular annulus? That is L1 B1 minus L2 B2 divided by what is the perimeter? 2 into bracket L1 plus B1 plus L2 plus B2. Okay. So by the simplification we get the equation as a 2 into bracket L1 B1 minus L2 B2 divided by L1 plus B1 plus L2 plus B2. So this is the equation for the rectangular annulus. आणि ज्या वेळेला when L1 and B1 same असतील आणि L2 आणि B2 same असतील, at that time we get the equation as a D is equal to 2 into bracket L1 square minus L2 square divided by 2 into L1 plus 2 into L2. Okay, ज्या वेळेला L1 is equal to B1 असेल and L2 is equal to B2 असेल, at that time we get the equation as a D is equal to 2 into bracket L1 square minus L2 square divided by 2 L1 plus 2 L2. Okay, A square minus B square काय असते A plus B A minus B. So from that we get the equation as a 2 into bracket L1 minus L2 L1 plus L2 divided by 2 कॉमन करून 2 2 कॅन्सल केलेला आहे L1 plus L2 आणि L1 plus L2 L1 plus L2 कॅन्सल होणार. So we get the equation as a L1 minus L2. ओके, ज्यावेळेला L1 B1 सेम असेल L2 B2 सेम असेल त्यावेळेला what is the equation for the equivalent diameter? That is L1 minus L2. L1 minus L2. ओके, देन राईट डाऊन फॉर अॅन्युलस. ज्यावेळेला एखादा रेक्टँग्युलर शेप असेल आणि त्याच्यामध्ये सर्क्युलर होल असेल तर फॉर दॅट वी हॅव टू कॅल्क्युलेट दी इक्विव्हॅलंट डायमीटर. ऑल ऑफ यू ड्रॉ दिस डायग्राम. Rectangular duct having length is L, center there is a hole having diameter is D, width is B. So equivalent diameter is equal to 4 into AC divided by P. 4 into AC divided by P. So 4 into what is the cross section area? L into B minus pi by 4 D square. क्रॉस सेक्शन एरिया काय असणार आहे? रेक्टँगलचा L इंटू बी असणार आहे, त्याच्यामधून सर्कलचं वजा करायला पाहिजे क्रॉस सेक्शन एरिया. मग सर्कलचा काय असतं पाय बाय 4 डी स्क्वेअर. सो 4 इंटू ब्रॅकेट एल बी मायनस पाय बाय 4 डी स्क्वेअर. आणि त्याच्यानंतर पेरिमीटर काय असणार आहे 2 इंटू ब्रॅकेट एल प्लस पी प्लस पाय इंटू डी. ओके, रेक्टँगलचा 2 इंटू एल प्लस बी आणि सर्कलचा पाय इंटू डी, त्या दोन्हीची काय होणार आहे ऍडिशन होणार आहे. So this is the equation for the when rectangle is there and at the center there is a hole is there. For that, this is the equation for the equivalent diameter. This is the equation for the equivalent diameter. Then again another shape is there, circular section is there, and in that there is a circular hole is there. So for that we have to write down the equation for the equivalent diameter. Okay, so equivalent diameter is equal to 4AC by P. So what is the cross section area? Pi by 4 D square minus pi by 4 small d square. And what is the perimeter? Pi into D plus D. Okay, so by the simplification, write down the equation for the for annulus for circular section. Okay, so here we have to stop. Remaining part we have to take in the tomorrow's lecture. Okay, so in next lecture we have to cover the local and average heat transfer coefficient. Then we have to go for the dimensional analysis. Then we have to go for the different relations. By using that we have to solve the some problems related to that. Okay, so that part we have to cover in the tomorrow's lecture. Okay, so thank you very much. All of you put your roll numbers in the chat box. Okay, sir, stop the recording, stop the meeting.